So this is a video about MTH 1035, and this is chapter 8. I just prepared a PowerPoint for the course because we couldn't do the face-to-face lecture, so I have to make a video in explaining some details for the natural nooks. So now let me just explain a little bit the purpose of this video. So you can see I will use a PowerPoint in helping me to explain the details, and I also use the lecture notes which is already available on Moodle. So I suggest you when you're watching the video, you should also have the notes with you. Okay, so because in many cases I would just refer back to the notes. So in order to learn the materials, or you have to understand what I'm talking, it's better for you to also have the lecture notes on your hand. So that's the purpose for the video. And also I have a PowerPoint, and I will upload it after I finish this video. So that's also helps you to understand the materials. So let's just start the video. So this is chapter 8, and the purpose for this chapter is about coloring a map. Okay, so actually we have 3 different topics. And the first one is I will tell you what is the meaning of coloring a map and how does it relate to a graph. So actually we can transform the problem into again a graph theory problem, and coloring a map is nothing but just coloring a graph. So you will see it, okay? And the second topic is about how we can apply it to some other problem. So actually it's not just for coloring graphs. In fact, we can use this concept, or we can use the theory to some other problem, including finding some schedules. Okay, so you will see it. Okay, so we have some application, and then I will tell you a method in doing the coloring, which is called the sequential coloring. So this is like an algorithm in coloring a graph. So that is the focus for this chapter, and I would do it one by one. Okay. So now let me just give you the motivation. So how can we color a map? In fact, okay. So actually, the goal in order to color a map is to, of course, we want to distinguish some different regions inside a map, because if there's no color, okay, so if I give you a map, if there's no color, sometimes it's quite difficult for you to distinguish different region. Okay, of course, if the map is not very complicated, then you can easily distinguish the regions, just one by one. But what about if it is a very complicated map? Then there are so many regions, and it's not that easy for you to distinguish or separate even different regions inside the map. So it's better for us to get some color. Okay, so but there's a problem. Okay, I mean, you want to color the map, okay, but how many colors you should use? Okay, so of course, if you have so many colors available, you can just color the region just as you like. Okay, you can color it in different colors. Okay, but what about if you don't have many colors on your hand? Then can you still distinguish the region using coloring? So that is one of the problem for coloring a map. So but we all agree that there's a number one criteria. Okay, so we should not color those neighboring regions in the same color. Okay, otherwise there's no way to distinguish the different regions. Okay, if you just color the region in the same color and they are next to each other, it's just confusing, right? So we avoid that. Okay, if they are just next to each other, then we color them into 2 different colors. Okay, so in other words, any two adjacent regions are of different colors. So that is one of the criteria in doing the coloring. So let me just give you an example. Okay, so that's how we can color a map. Actually, we don't really need that many colors. Okay, even though there are so many regions, sometimes we don't need that many colors. So let me just click it. Okay, and you will see that funny example. So you see in this diagram, actually it's a map of the United States. So there are different states in the United States, you know that. And how can we distinguish it using different colors? Actually, this is the way to do that. You see, for example, these two regions, so one is in blue, the other is in orange, and they are next to each other. And the point is, now I can repeat the color, okay, as long as they are not adjacent to each other. So this is blue, this is also blue, and that is blue again. So there's a very funny question. Okay, how many colors do we really need to color a map? Okay, so this is a very, very challenging question for mathematics. Okay, and it turns out that we don't need many. Okay, in fact, we just need four colors to color a map. Okay, but we will see that later. Okay, but you see, this is exactly the problem we have. If we have the map, we have different regions. If we want to distinguish different regions using different colors, actually, we can just do that coloring. Okay, so now that is one example. Now let me go back to the PowerPoint. Okay. Now, well, we can consider so many examples, just like the example I just shown you. Also, you can look at the notes. Okay, so there are many examples. For example, this one, if you go to my notes, this baby map. Okay, so there are only 5 regions in this diagram. Okay, so now for that so-called map, okay, 5 regions, how can we color it? Okay, so of course, if you just follow the rule, you can easily color it without any difficulty. But just think about it. If the map is very complicated, we better develop a better method to do the coloring. Okay, we just not just solve one problem. We want to solve as many problems as possible. Okay, so that's the purpose. So let me just go back to the lecture, to the PowerPoint. So in fact, the way to do the coloring or to solve the problem is to transform the map, okay, into a graph. Actually, it's exactly what we did in the very beginning of this course, because remember, we have the 7 bridges problem, and for that problem we have a map, okay, but we don't really solve that map problem, but we better translate the whole thing into a graph. Okay, and actually we have a similar situation here. So first we identify each region, okay, a vertex. Okay, we just change everything to be vertex. Okay, and remember, for graph we have 2 components, namely the vertex and the edges. Okay, so how do we put the edges into the graph? Well, that is the way to define the edge. So if we have 2 regions which are adjacent to each other, then we connect the corresponding vertex by an edge. So because of that, we can easily get this graph. Okay, so very, very easy. So we just translate that into this graph. Okay, now we just do our problem on this graph. So everything now is just on this graph. We don't even have to refer back to the map. Of course, after we solve the problem, we can just go back to the original map and get the corresponding colorings. But at this moment, we just focus on the graph. Okay. Now, how can we color it? Okay, of course, as I said, if you have as many colors as possible, For example, if you have a, okay, so there's typo. So if we have a graph with n vertex, then we can always use n many colors to color it. Okay, so it's trivial, right? Because how can you distinguish those n different regions? Oh, if you can use n different colors, then of course you can easily distinguish those regions. But of course, it's not very smart, okay, because you just spend so many different colors. For example, if you what about you have 1,000 vertex, then how can you get 1,000 colors? Okay, and in fact, as we have seen in the previous example, even though for the map of the United States, we don't really need that many colors. We don't need like 50 something colors to color the map of the United States. So we can do the problem way below the number of vertex. Okay, so we can use quite a little colors compared with the number of vertex. And as I said, to save the cost, okay, we want to use as few colors as possible to color the map. Okay, because not just about the cost. Sometimes because it's just not practical. Okay, how can you get 1,000 different type of colors? Okay, so for example, if you have 1,000 many vertex, so for example, if we want to color the map in our example on nodes, so that is the graph I just mentioned. So this one, how many colors do we have? Actually, you can just try it. In fact, you can use less than 5 many colors. Okay, so even though it has 5 different points, we can just use 4 colors to color the vertex. Okay, so you can do that. You can try it. And in fact, in my notes, I gave you the answer already. So now how can we? Okay, sorry. So how can we really color it? Okay, of course you can use the words. So like, for example, you label the vertex by some names, like you call the vertex red. Okay, and then okay, for example, let me just go back here. So for example, if you want to color this graph, for example, vertex 1, which you just put some name like red. Okay, for number 1, maybe number 2 is yellow, and number 3 is blue, something like that. But as I said, it's a labeling. Okay, so even though we keep saying coloring, in fact, it's nothing but just a label, so, as a name. Okay, so to save, okay, because we are lazy, so to save our energy on those naming process, we just use alphabets for the color. Okay, for example, we use alphabet A for the color on vertex 1, and the alphabet A for the vertex 3 as well. So and so on. So we use alphabets for the colors. Okay, so A, B, C, D actually they mean the colors on those vertex. Okay, so as just a name. Okay. Oh, sorry, I just have to go back. Okay, so we're back here. Now, actually, if you have a very special, if you have some special graphs, okay, so something called simple graph, we can always color those simple graph with the number of colors, okay, needed less than or equal to the maximum degree. Okay, actually, it's nothing but just the theorem I mentioned in the notes. So it's called the Brooks theorem. Okay, you can try. Okay, but of course you have to understand what is the meaning for simple graph. Well, I also gave you the definition in the notes. Okay, a simple graph is just an undirected graph that has no loops and no more than 2 edges between any 2 different vertex. So in other words, you just can think of it like you don't have so for example, you don't have a loop, okay, or for example, if you have 2 vertex, there's only at most 1 edge between any pair of vertex. So that is the very simple meaning for simple graph. Okay, so if you have a simple graph like that, then in fact you can just you can easily color it according to the degrees. Okay, you just look at the degree on the vertex, and in fact the maximum degree always tell you the number of colors. Okay, so except actually there are some exceptional cases. If the graph is complete or if the graph is cyclic, then actually you need more. Okay, so you need the maximum degree +1. Okay, so you see why it's +1. So let me give you the reason. Now, for example, okay, so if the graph is complete, okay, if it is complete, okay, if it's complete with n vertexes, okay, then all we need is how many colors? Well, we just need n many. So think about it, because all the vertex, okay, they are linked up. So in other words, there's no way for you to use two different colors for two different vertex, because they must be linked up by exactly one edge, okay, because it's complete. So that's why if you have n many vertex for a complete graph, then you must use n many colors to color it. There's no way you can do it less than n, okay, because of the reason of I just mentioned. Okay, so that is a special case. And on the other hand, okay, if you have a graph which is cyclic, okay, cyclic means is a circle graph. Okay, so that means you can always put those vertex on the circle. Okay, if the graph has n vertexes, okay, then depending on the value for n, then in fact you can use 2 or 3 many colors to color it. Okay, so think about it. If you have 6 vertex, okay. Oh, okay. So let me use another example. If you have 4 vertex, of a cyclic graph, then how many colors do you need? Well, you can easily see that you just need two different colors to color the graph, because you just color the opposite vertex in the same color. Okay, because the opposite vertex, there is no edge between the opposite vertex. Okay, just imagine you put those 4 different vertex at the corners of a square. Okay, then you exactly need two different colors to color the vertex. So actually you can do it for the case of 6 vertex or 8 vertex. You simply color those opposite pair of vertex in the same color. Okay, then you can see actually you just need two different colors to color the map. Color the graph. Okay, that is the case for n being even. Now, if n is odd, then we have a different situation. So now, a very simple case is if you have 3 vertex. If you have 3 vertex for a cyclic graph, then you can put those vertex on the corners of the triangle. Okay, so for example, you have a triangle, you have you have 3 vertex, okay, of that triangle. Then how can you do the coloring? Of course, you must use 3 different colors, because they are all linked up together. Okay, so by doing that, you can easily see you need more. Okay, so so try to think about the problem. So see if you understand why we have these 2 different situations. Okay, it's not that difficult, I would say. Okay, so those are 2 special cases. Now, on the other hand, okay, if we have a graph which is planar, okay, so what is the meaning for planar? So roughly speaking, you can just think about that planar graph as a graph which can be obtained from a map in the real world. So as I said at the very beginning, how can you get a graph from a map? Okay, you just use the vertex for the region, and then if the 2 regions are adjacent to each other, you put the edge. Then you can always get a graph from a map. Now, if the graph is obtained from a map in the real world, then it must be planar. So roughly speaking, those are the graphs that you obtain from maps. Okay. Then, in fact, okay, we only need 4 different colors. Okay, so this is I just told you at the very beginning for the video, because well, there's a name for that theorem, which is called a 4-color theorem. Okay, so let me show you. I mentioned that in the notes. 4-color theorem. All planar graphs can be colored by 4 colors. Okay, So of course I won't give you the proof, because in fact this is a very challenging problem in mathematics. Okay, it just puzzled those mathematicians for hundreds of years. Okay, and in fact the proof, okay, so there's a proof for that. Okay, but the proof is so long. Okay, it involves I don't remember, hundreds of pages, and we even need the computer to solve the problem. Okay, why do we need the computer? In fact, the mathematician able to identify those cases, but still there are like thousands of different cases that for the pentagraphs. So they need the computer to exhaust those possibilities. So that's why it's very long, and it's called the four-color theorem. Okay, so any pentagraph can be colored by at most 4 different colors. So exactly that example I showed you before, I can show you one more time. Okay, this one. Okay, even though you see this is so complicated, you can count the number of colors. Actually, you just need 4 many. Okay, so this is the 4-color mapping theorem, four-color theorem. Okay, and it's very challenging, but of course I won't give you the proof here, because even though I don't really know how to show you the whole proof because it's so long. Okay, so this is the first part of the video about coloring a map. Okay, so this is the first part, and you can click the other video for the second part.